Today's video is sort of a test. I'm experimenting with different kinds of formats that I make my videos in. If you like the old format, or if you like this new one and want to see more of it, let me know. And without further ado, let's get into the video. Welcome to a video about aliens, chemistry, astronomy, and geoscience. But wait, don't click off yet. This will be cool. During the course of this video, I'm gonna prove that aliens exist without even hardly talking about aliens. Now, I know, we can go back and forth all day about whether there's any proof that aliens are actually real. So let me just go so far forth that you can't go back. First off, let me describe to you how life started on our planet so we can then apply that elsewhere. Now, let's look at the most abundant substances in the universe, directly matched up with what we're made of. First on that list is hydrogen. It's the most abundant substance in the universe. Second is helium. Third is oxygen. And fourth is carbon. Now, carbon is the most chemically fertile substance on the periodic table. You can make more kinds of molecules with carbon than all the other molecules combined. Now, here's what we're made of. Everyone knows our bodies are 70% water, which is H2O, which is 2 hydrogen, 1 oxygen. So of course, our bodies are mostly made up of hydrogen. Second is oxygen. And then third is carbon, as in carbon-based life. And fourth is, trace elements, like nitrogen, stuff like that. Helium, though, is missing from that list because helium is chemically inert. It's the bad apple. It doesn't get along well with all the other kids, and it just sits there and remains inactive. Hold on to that information. Let's see how long it took for life to develop on Earth. Let me rewind the cosmic clock. 4.5 billion years ago, the birth of our planet. Now, let's look at the earliest concrete evidence for life, which is 3.5 billion years ago. So that's about a billion years. It's pretty good. That's about a fifth or 20% of the entire existence of Earth. Most people would start the clock right here and be done with it, but I'm never done with it. What if I told you that recent fossil records have pushed that number back to 3.8 billion years ago? So the amount of time it takes for life to form from the beginning of Earth to the first evidence of life is a little under a billion years. That's like 0.7 billion years or something. Well, now you may say, oh yeah, so what? You shaved a couple million years off. Potato, potato. Well, hold your horses. In the early solar system, there was interplanetary cosmic debris everywhere. So for the first 600 million years of Earth's existence, it was getting heavily bombarded by asteroids comparable to the size of the one that took out the dinosaurs, but monthly. On a cosmic scale, that's pretty much around-the-clock devastation. Because of this, that means that the surface of Earth was so hot that molecules could not yet even form because of the little fact that molecules break apart at high temperatures. So, Life didn't even have a chance yet. We can't start the clock right here. You have to wait for the surface of the Earth to cool down, which was approximately 3.8 billion years ago, shortening the amount of time it takes for life to develop all the way down to just 200 million years. We just went from a billion years to 0.7 billion years, all the way down to 200 million years. When life had a chance to form, it did. Now, with that information, we can start to apply it elsewhere. Given the odds that life as we know it is made up of some of the most abundant substances in the universe, it highly increases the likelihood of life forming somewhere else in the universe as well. Especially considering we've discovered a ton of Earth-like planets in just the Milky Way galaxy alone. Now, that doesn't mean that life can only form on Earth-like planets that are in the Goldilocks zone, which is, it's not too close to the star and it's not too far away. It's right in that sweet spot, which is where we have the greatest chance of finding liquid water, which is the key to finding life. Life is pretty adaptive and durable. Wherever we find water on Earth, we find life. Even in the most unlikely of places, like the Dead Sea, which is 8.6 times saltier than the ocean, there are minuscule life forms dwelling at the bottom, such as bacteria and microbial fungi. So if water's the key, then let's look at a place that's in our solar system. Jupiter's moon of Europa. On this moon, there's a crust of ice enveloping it, with a liquid water ocean beneath it. Now, you may ask yourself, isn't it too cold? No. In fact, as Europa orbits around Jupiter, and as it passes by Jupiter's 78 other moons, it changes shapes due to gravity. Everything's constantly pulling on it. Because of this, energy is being continuously pumped into the moon, which heats it up. This is coupled with the fact that ice insulates. That's why fish don't die during the winter when the lake freezes over. With that information, we can now broaden our scope of where life could possibly form, which increases the likelihood of aliens existing even further. And that doesn't mean life has to just be carbon-based. But first, I have to bring you up to speed. I have a working hypothesis that the further you go in towards the center of the universe, the less likely you are to come across complex life, or even any life at all. This is due to how stars are made. At first, there was only hydrogen, and then helium, and then stars started using the hydrogen and the helium, which then expanded and died out, and turned into quote-unquote space dust, that then started coming closer together because of gravity, and then boom, they formed beautiful, even more complex stars that cause different elements to be made. And this is happening all the while the universe is expanding, so the more complex stars are further away from the center of the universe, which means more and different complex kinds of bonds between different elements, which means more chances for complex life, which means life could possibly be made of a whole range of elements. Ever heard of silicon? Maybe not. It's a metalloid that can conduct electricity even better than most metals, because at high temperatures, metals stop conducting electricity, but silicon doesn't. What if I told you that silicon is directly under carbon on the periodic table? So basically,
I'm saying androids. That concludes today's installment. Let me know which format you guys would like to see more of. Stay tuned for more. I hope you enjoyed.